Так, ну что ж, давайте продолжать, и, соответственно, Александр нам расскажет.
So we can continue, and Aleksandr will tell us about his experience of migration from Oracle to PostgreSQL. Hello, colleagues. We will have two Aleksandrs actually. At first I will speak in front of you, and after that Aleksandr Chirkov will speak. Both of us are from Kazan, from Bars Group company. Our company develops management system for state sector. And we also had this issue of import substitution that was not easy for us. And actually our company manufactures a lot of products. There are a lot of products that were started in early 2000, and all of them used Oracle. So, step by step, they migrated to Postgres, and it was quite a standard way of data transfer, and tables were described, and stored procedures were amended manually for them to work with PostgreSQL. These were simple operations. All the systems worked with ORM, and there were no specific problems here. So at some point there was only one information system that was not transferred. Actually, it was not possible to transfer it in such a way, and manual transfer turned out to be impossible due to a lot of procedures. And we had to use standard way to automatically convert the table and schema of this database from Oracle to Postgres. So let's look at technological stack of our information system. It has two parts. One part is PHP and the other part is Oracle. In Oracle you can see the number of tables, views, and triggers, 300, 3700, 3400, that's a lot. Our procedures and functions are not numerous, 620, but there are packages in Oracle, and the guys that were developing this system really liked this concept. The mechanism in Oracle that is not present in PostgreSQL. These are packages. This is logical units of specific procedures and functions in one place, and the internal state of this package that can use these procedures. So there were 2,800 packages, and every package had up to 20 functions, from 4 to 20 functions. And there is a block, for example, for working with contractors and specific package for this block, and you can add, delete, modify, and do this kind of operations. And there are other operations like add something complicated in a complicated way, so there are various functions here. And we can multiply this number by 10, and this will be the total number of stored procedures. Most views and triggers were written in code. They were written manually. And the second part is PhD, about 1 gigabyte of source codes. And inside there were forms, dynamic forms. Well, they are not really different. These are structures where you can find descriptions on PL/SQL. They look like that. You cannot see it well, but I can read it for you. These are examples of PHP codes. This is the standard component and its definition. And after that, declare is stated, and this is anonymous block of Oracle. So, PHP part of this information system looks as follows. PHP is responsible for the order of forms and visual interface, and all the business actions that take place in the system are fulfilled in PL/SQL. So this 9,000 plus 1,000 of forms also represent storage of PL/SQL code, and in one such form there can be several descriptions of this code. For example, description of the way we take data, the way we save data, validation, all of that is done on PL/SQL, and PHP doesn't have any business logic, it works with data only. And what makes it more complicated? Well, actually, here you can see component select that selects the data from database, and this select has specific parameters, specific cast temple, so it's stated that this is select. It goes on, and at some point we see add, if, and a condition. And in the runtime of this form, for example, if backup was assigned in a specific way, we add something else to this select. I mean that there is no source text of the procedure in terms of select function. There are some insets, some templates that in the runtime actually transfer it into specific representation in PL/SQL. I will explain you why it was difficult for us. So we tried actually transferring it, and at first it failed at the level of tables because there were comments to the fields of tables, and these comments were important for the system because they are additional meta information that is used in the engine. So we decided to reject our TPG, and we needed to have a strategy for us to transfer these functions and procedures as well as anonymous blocks, to transfer them from PL/SQL to PGP/SQL. So we devised this strategy. This is a huge area of data. It was not possible to process it manually. It would took us too much. And there were attempts to use several iterations and transfer the system manually or semi-manually, but it wasn't possible. So we decided to develop an automatic converter that will transfer it, that will use grammatic parser and build trees for every PL/SQL structure. We will see this tree process, this tree for PostgreSQL. After that, we will record it, save it, and these will be converted in a statical mode. So it takes Oracle schema that was uploaded by SQL developer. It will parse it through the converter and get the scheme that is ready to be uploaded to PL/SQL. And there are also anonymous blocks, and most likely such blocks cannot pass through grammatic parser. So only in the runtime we can see specific text of the function of the anonymous block that is to be executed now. So our goal was as follows. We decided that all PHP parts would remain the same, and in the runtime, when the form wants to be saved and downloaded, these queries that were just formed in the form of a specific anonymous block that would be fulfilled in Postgres actually passed through the similar converter that was functioning in dynamic mode. This is a separate microservice. It receives texts in PL/SQL and it provides text on PGP/SQL. This is microservice. And for us to make sure that it works, we were to automate it so that everything would be assembled when you press just one button. It is for us to work with the current scheme, current state of this converter, so that we would be able to assemble it, test it, and kill it in a very fast manner. Let's move forward. What should we have? As a result, PHP part of our information system remains the same. Connected to PostgreSQL is added here, as well as connected to microservice. And in real-time mode, they answer the queries on procedure conversion regarding the anonymous blocks that had been recorded. PostgreSQL includes completely converted schema. The microservice that provides broadcasting in dynamic mode addresses PHP and PostgreSQL. So it was very dynamic in text procedures as well, and there was such structure as execute and immediate. So inside PL/SQL code, another code was formed and it was to be executed. And grammatic parser saw it as operations with strings, and these operations were to be executed afterwards. So we should intercept these kind of issues when they are trying to be executed in the current DBMS. We should address the microservice, receive the text of this structure for PostgreSQL and execute it. And Elasticsearch is the place where we recorded logs and debugging information to see what was going on. So let's start with ANTLR. Have you encountered this issue? Actually, this is another tool for language recognition. This is a utility written on Java that can do the following. It receives grammar of a formal language. And TLR makes runtime on different languages out of this grammar on Java, on C++, on Python, what else, C#. So this is runtime. This is a set of classes that you can take inside your application, and you will get a parser for the language that you gave to until R during the first phase. And the runtime generated by ANTLR includes three main things. This is lexer. So we can imagine PL/SQL procedures as a set of symbols, and lexer takes this set of symbols, they pass through it, and as a result, we receive a set of roots that would work out for this language. And after that parser works out, it recognizes the language. I mean that in cybernetics, there is this task of language recognition, when we want to understand whether this order of symbols is valid for a language that was formally described in terms of grammar. Apart from that, there is an interesting issue that computer scientists develop is as follows. The mechanism for understanding that this order of symbols is valid for a language, and this algorithm can build abstract syntaxes tree of these issues. So it can build a tree-like structure. Imagine that this is 1 plus 1. 1 will be a node on top, and there are two daughter nodes. And this is an abstract syntaxes tree. It can do that. And besides, it can also generate a software that can help us walk across this tree. It's important for us because we should walk along this tree and build a tree that would be a bit different, but it will be used in Postgres and saved. So let's see the way it works on the example.
So we have a hierarchical query which has no analog in PSQL. So here we say select from a table with where, connect by, and start with, showing that we remove something and hierarchically explain the input conditions which we start our hierarchy with, and further down. In Postgres, it should turn into a common table expression, CTE, non-recursive, with a separate start part, recursive part, and CTE as it is being shaped, and the final select from this temp table. This is a standard topic for those who migrated from Oracle to Postgres. If you could build the expression tree for Oracle query, we would see that there are certain conditions written by the original iteration, how we shape the starting part, how we shape the part that will be recursive, and the final list of fields available for the hierarchical query. We need to print it in. Let us see this query from the PSQL language and grammar. Here is the repository at GitHub, and inside there is grammars. Under the repository, where there is a lot of grammar for all languages, for all cases, enthusiasts from around the globe send examples. So we found grammar for PLSQL there. So this is what it looks like for our hierarchical query. BNF forms to describe grammars. It's the same, but in a more understandable way. Our query block begins with select, distinct, unique, and all, with a question mark, asterisk, or a list of elements. Each of the elements may be represented by some expression, followed by alias. the way we write SQL queries written in this language from clause in query grammar. You may find hierarchical query clause, connect by, condition, the start part. This is the description in the form of grammar in PL/SQL. Moving on, if we launch this grammar form runtime and launch into a procedure, we will see the following in the debugger. This is the context, the current context. Here is select. Query block is the one we're working with. Here we have child with terminal node of select, which corresponds to our grammar here. These strings, these rules are part of the tree. Here we have description of selected elements, from clause, where clause, and the subtree corresponding to the hierarchical query with terminal nodes connect and by, and then we see the subtree corresponding to condition. So all this is written here. This tree is stopped at expression context, although it goes all the way down with very complex rules reflecting the current work with the expressions. So we try to walk around this tree. This is what we have in Oracle. Here we have the subtree corresponding to the hierarchical clause, start part and condition. So we take those blocks and shape the syntactic tree for PostgreSQL. We have the node which represents common CTE. Inside there is a recursive space to insert recursive and non-recursive character. This is how we get the tree. If you just print it in a trivial manner with indents to make it look beautiful, we get a workable and operable query automatically generated to perform in PostgreSQL. This is the simplest example, but in the same fashion we can disassemble tables and expressions made of thousands of strings. There are packages with thousands of strings, and this is how you can disassemble them, how you can understand grammar. And now let me hand over to the second Aleksandr, who will speak about special features, about the ability to see hierarchical queries, to understand which expressions it is made of, and also you need to compile an accurate expression for PostgreSQL. So Aleksandr will tell us how to do this. Can you hear me? My name is Aleksandr. I will speak about technical features of working of our converter operation. When we decided to write our own converter, we had to upload or download the database structure from Oracle. So we did this through Oracle Developer. This is the structure, and we were happy with it. We only added some sections identified in red color before, first cycle, and after. I'll explain what happens as we process each section and what is stored in this section, in each section. So the first section is before. Here we had extension Oracle FSC and a set of standard procedures required to be loaded to Postgres before we process the full schema and put it in it to be able to launch it. After the first launches, we had issues with recursive casts, and we couldn't resolve it. After a couple of hours, we decided not to use A.Kvaratskhelia and use only functions and entities from that extensions that were necessary for us. So we added our casts and operators to work with datums. As we subtract two datums, we had the variable of the type, number type, and in Postgres we get indent. To make them friends, we had to write our own casts. Here we also store analogs of system tables written by head, user objects, user triggers, DBA, procedures and functions. We certainly wrote analogs of standard functions, additional functions to process some structures, to work with XML with tables announced as table of. And here we also store analogs of packages which we implemented. The most interesting one is DBMS SQL. This is a package for dynamic processing of queries in order to obtain values from tables by the number of column. We've had a lot of queries like that, thousands of them. They came from different fields of tables into one final query. It was written on Oracle. To rewrite it, it would have taken us 2 to 3 months. We did not have so much time, of course. We wrote implementation of our own package, which calls function for NPL Python, sends to microservice, sends it back in the Postgres acceptable view, and then caches the outcome of the conversion into several tables. And this query will be taken from those tables. We had some lag in performance, but it wasn't very critical. Then we process tables. Here we have standard creation of tables, comments to tables, and comments to each column. Here we assemble data from all types, from all table columns, so that in the future we could bring some entities to a single type, to one type of data. So if we transfer several columns of different types, we had to cast those parameters. We also have records types with the fields with inherited types from some other column. And Postgres was not happy. It said, give me a native type, so we had to do it. And for tables announced as global temporary, we additionally generated procedural codes which creates this table. Here we have examples how to convert global table. We created a table first, and then we create a table in the public catalog. What is it for? Do you know? Do you have any ideas? Below is an example. If some variable has a tuple of row type, then Postgres will fail and will not be able to create this table and will not say, create this table for me. So in public, we create this table, and at any operation with this table, we have this procedure on top. We bring this procedure on top. The next section is data indexes and constraints. They are transferred without problems and do not affect the operation of the converter. Syntaxes gets different. Some key words are changed, which are, we put them in parentheses. And some disable and enable. Disable are not created. Enable are sent to Postgres. Then we process types. Types are announced as objects, so they are transferred in the same form, but they are put into the anonymous unit to be able to see exceptions if we have similar types. So as we repeatedly load the script so that to avoid errors, we simply process it as an exception. Moreover, we have types announced as table of. On the internet, you can't find any information about it. we now know how people handle this. We tried different ways: JSON, variable tables, iStore. We create dictionary type data to work with the dictionary type. This is where we have dictionary type. For that, we create dictionary set, dictionary get, full analogs of Oracle structures. This is an example of how to treat this type. We initialize to dictionary created for the types whose keys are strings, dictionary create varchar. This is an example of how to work with these data, and we cannot select to this variable. We have hstore, so we cannot inhabit it. We create a temporary variable, DTP FSS type, then select there, and after the select outcome, then through dictionary set, we send it to the appropriate place. Then we process first cycle, which we added on our own, which holds the fold of procedures. In Oracle, if we see a function without parameters, Oracle will call this function without brackets. In Postgres, we should add those brackets. But how to differentiate a variable from a function if there are no brackets and if we do not know about these functions? So the converter will do nothing, and at the compilation process, Postgres will just stop and say, I do not recognize this variable. And parameters of this function are needed for the right cast in order to find the function in the right place, to find the appropriate functions, even if the system is overloaded, and those parameters are cast to the types of those functions. The next fold is packages. Packages are processed. Here we create schemas. We collect information on functions and procedures for the same purposes as in the previous folders, so that we know about those functions. And here we also process global variables. This slide shows how we fight it. They're implemented through getter and setter, which call upon standard Postgres functions, setConfig, and current settings. Version variable, set version, and get version are created to keep the values. It works similarly as table of. So a temporary variable is created, it is selected, and then through set version function, it is saved. Then we process function and procedures. 3 sections: processing of parameters. Standard types are replaced with Postgres types. Postgres, as we find a parameter, it has a default value. It asks to make those parameters 0. Number 2 is process declare. Here we change the type of variable, not to a native type, but to our own type, which after processing of the body we find and change. We had iCursor variable. It was initiated through this function. We replace the call of the procedure and the variable to be able to keep information there on the number of strings, on the current values of the current strings. So we do that very quickly. Creation of types and subtypes, we do that as in the previous section globally within a package. How to create internal functions and procedures. Here is another example. Here is an internal procedure called REPL. We use it in decode. So we bring it to the level of a package. We add a prefix of the parent function to its name. We add other variables and parameters of the parent function. And then it is called upon together with all this. We do this because internal functions and procedures can change the values of those parameters. Then we process body. A lot happens here. A lot that doesn't fit into this presentation or on this slide. We also process pipeline of functions. For some function, we use flex table. We cannot find insert, delete entities, call of certain functions there. But these are interesting. Here we add variable cycles. In Oracle, you don't need to announce it. In declare block, you add intermediate variables. We process exceptions here, similarly as in Oracle exceptions. Exceptions are no data found and others. For all selects, we add strict to catch those exceptions. Connect by start if is replaced on with recursive, plus it is replaced with left outer joint. And we select everything according to this slide. We wrap it into can cut function so that the resulting string works well. So we also do wrapping with new if too, checking if at the entrance the variable is an empty string, the null is returned and the expression will be correct. Then we replace the code with a case, cast, require the same type, and we do this if where possible. And also we change the behavior of some standard functions. We may replace them with substar2 and make sure it operates as in Oracle. To have the operation identical both in Oracle and in Postgres. Here you can see default parameters. They're added. You change the variable type, add prefix, plus replaced with outer joint, etc. So a lot of replacements. The next section is views. Nothing new as compared to the previous section. I can only say that in Postgres there is no structure create or replace force, which creates views regardless of dependencies. In Postgres, in Converter, we build the dependence hierarchy and load views into Postgres in this given order. Then we process triggers. So we create functions and create triggers themselves, replace some key structures, and in the end, we add the block with the numbers, which returns the old of the new value. The next folder is after, where we have some entities that could not be converted by the converter. Here we have functions that will work faster, so we launch them, convert, but if it is slow, then we put it in after. To automate it, we rewrite this function, add to this folder, and next time during conversion, everything is going to be all right. And the final section, it is easy to rewrite it by hand than to add converter, because otherwise we'll have to work on the converter for 2 weeks, but to rewrite a function it takes only 2 hours. So we rewrite this function, put it in this folder, and put a task saying that we need to work on a given case. So we have converted the database, and we have the back end where query come from, and they should be processed. These are selects and anonymous blocks. Selects remain selects. Anonymous blocks in Oracle, which can return values externally, are non-existent in Postgres. So we convert them and change them. We also use bin variables. In backend, we add two new classes, log, cache, work with big objects, because the driver did not let us work as we wanted. We wrote our own realization and the connector Postgres. Also, we could support two versions of the project. You can write part in Oracle, put through the microservice, or you can use converted results, put them in a given form, indicate that it is Postgres type, and then it will be directed to Postgres. Manual work. Well, functions and procedures with a number of parameters in excess of 100, we reassembled and replaced it to 300, but at the same time we decomposited those functions, change of calls, etc. We have functions and procedures with the same names and parameters. Oracle allows it, Postgres does not, so we change the names manually and change their calls. And the converter will eat it very well and convert it. The biggest pain was alias of tables, so we could do nothing about it. When we have alias and it refers to the fields, Postgres will say, I don't know what you want, which table it is in, please correct. So those things were in anonymous blocks and they were rewritten, sent to Git, everything was saved and the converter worked well, could process it really well. Out parameter functions. Those functions cannot return values which are different from the out parameter. We had to rewrite those functions, replacement with procedures, and changed their calls. Thank you. Alexander, thank you. We have time for some questions. In dynamic SQL, how did you process the parameters? As literals or by parameters? There is a method, and we wrote some regular code, which sent it to the converter converted, and then we got it back. No, this SQL, you had to launch it through execute in the paperless SQL. Execute only takes position parameters. Yes, we changed it for position parameters. With the converter, we understand the order which they came to us. It returns this SQL request with the same order. So as you launch execute, you hard code those parameters. No, we did hard code them. No, those parameters will obviously execute. Yes, that's right. You've done a fantastic work. I guess we could give you our work and you would do it, and we could do not work within a year. Well, this merge operator, external tables, as to merge, it is converted to the same analog. To insert, and some structures are added, it is possible to process it in progress. What about Oracle utilities? we understand the tail file is not safe, but maybe some external tables. We did not have any external tables, but some packages, we wrote implementation for them. We even have call of microservices from the database. We processed them. So anything that could be implemented with our converter, we tried to do it automatically. And we kept the same signatures. Two questions. When a null column was a unique index, did you have such instances? No, we didn't have such columns. So the system which was subject to conversion is in production now. Yes, that's right. It has been in operation for 2 to 3 months. Also, we do development on Oracle, so the functionality is written in Oracle, because the Oracle team, it is still working. And the Postgres team adapts everything, so the converter does things automatically, and the things are maintained by the team. 150 commits every day. How many people participated in development of this converter? And how much time did you spend? 3.5 people per year. So we worked for a year, and we had 3.5 developers. And certainly some unique experts from Oracle and Postgres who helped us with different special things. We were busy working with the back end. So 3.5 developers plus DBA. Yes, correct. And the last question. So the second row, please. So I guess how many schemas did you have? 2,000? How to open them? With which tool? Any tool. Navicat, PG admin. All this works well. Can it really open 2,000 items? DBL does it really well. We didn't have any issues with it. Well, as I understand, there is no access differentiation. No, but users within the system were the Postgres users. So each user, as we created a user in the database, and the users were given with certain rights, and those rights were limited with certain packages. So we created Postgres users. What about the package initialization? So the package contains variables and the body. Where did you insert it? I don't think we had it. But a package has variables and the body of package initialization. Initialization body, we only had procedural functions and global variables. What about the procedures themselves? Are they with development rights or with the caller's rights? The caller's rights. How was it possible to test this system given this big amount? You probably didn't test it. No, we had an automatic tool for testing. We installed our proxy service through Oracle. We processed the queries, And then we did the same with the same sequence on Postgres. And the second testing is when we had a lot of people and people tested everything manually. We decided not to show it in the presentation but we have a full farm. When a person comes in, enters, an automatic CI is created, URL port is used to enter the system to see how it works. And also, this person can get into Docker, an information system is deployed, he checks the scenario. So this farm is a proxy server, registers all queries, they're processed in the same sequence. Then we analyze it after each execution, then we measure time, we see whether Elasticsearch contains any mistakes and how much different the Oracle response to the Postgres response. If the difference is big, then we say the response is wrong, and then we do manual testing to assess all this. Is it a commercial project? No, this is to make our information system operable. Do you do commercial projects? Well, this is not our area of responsibilities. We are developers. We do what we're told. But I think it can be discussed. The rest of the questions will be discussed offline. A short question. The system speed. How different was it? No, it was almost the same. So 95% of queries were processed within a plus or minus 10% of time. The remaining 5% of queries we developed further. If it was a complicated query, we modified the Oracle part so that it could be converted into the structure that could work faster on Postgres. For some queries, we had to put it in the prior. You will always have those 5% of queries for which you will have to do extra work.